In the previous video, we actually stopped here and defining that C1, C2, C3 are all these numbers. Alright, you can actually leave them as the answer it is. Alright, now I'm gonna explain in terms of graphically how this thing is doing. What is actually this thing? Alright, yeah. Still remember back, our general equation comes from where? It all comes from our ds is equals to us over es, which is this transfer function over here. Correct? Now, if you want to go a further step, alright, since we know our C1, C2 and C3, alright, since we know our C1, C2 and C3 for backward and forward loop, okay, now we are actually keen to solve for the rest of the system. We want to know how does the graph works. If you still remember, we are actually keen to, because these are the points, right, we're actually keen to actually somewhat create a continuous system based on our points. So what can we do, and visually what are all these things? To start, I'll just start off with stating that this UK, EK, and even EK plus 1 and UK plus 1 are all certain functions. They all individually have their own function, maybe like k squared plus 2, then this may be like 2k plus 3, something like that. Alright, I'll just leave it over here. Alright, I'll just leave this equations over here. Later on you'll know how does this go like. Alright, when I start the machine, there will be a signal that goes into the system. Alright, there will be a signal that goes through into the system. And this signal is actually EK or ES. I mean, input is ES, but we are now talking about EK. Alright, so therefore, if you want to look at the graph, EK will be somewhere over here, for example, alright, somewhere over here, and this point, it's coming from this equation, alright, and in fact this first signal, I should say that this first signal input, alright, I will call this K1, or maybe I just put it over here, K1, alright, this is the first input into the system, and when I put K1, I will say that maybe this is like 5, for example. Alright, so 5 times 2 is equals to 10, so 13. So this point will be plotted into the system over here, for example. Alright, including times C2 lah. For example, C2 is 1 if that's the case. But I just want to convey that yeah, this point reflects this position over here. Alright, this function over here. This is K1, alright, and K1 comes out into as an output Euler, which is UK. Alright, so when it comes out, alright, because of coming out from the transfer function, it may have a certain different values. Alright, so this different value, I'll just plug it in. Alright, so if this is 5 squared is 25, alright, 25 plus 2 is 27, so I'll just plot the values over here. So this is the output of K1, okay, so this is output, this is input. Alright, now K1 goes out as an output, K1 will also feedback, right, when it feedbacks and interact with the initial K1 input, alright, this means that at this new point over here is called K1 plus 1, which is also K2. Alright, so I'll just define it over here for better setting like this. Alright, K2 is equals to K1 plus 1 subscript, and the values maybe in this case maybe like 8, for example. So this K1 plus 1 will actually be input over here. Alright, so in other words, K plus 1 is in fact K2, which is the new coming in signal that is going to fit into this thing. You get what I mean? So now we are talking about second round. First round, K1. Second round, K1 fixed back here will become K2. And therefore now we are talking about it. Alright, when we sub in K2 or K1 plus 1, or I mean k plus 1, sorry. This means that, for example, this is k, right? So this k is in fact k1, k2, okay? And therefore, meaning k plus 1, in this case is this one, okay? So therefore, if I were to sub in this value, I have 32 plus 5 is equals to 37, for example, and this is a plot for k2, alright? So this is somewhat the new input. So far so good. And this new input, k2, will be fed into Euler as an output. Alright, and therefore it's somewhat stubbing in as 8 also over here. So this is 8. Alright, this is some values lah. Alright, in other words, I have no equation because this one, alright, this one plus this one plus this one will give a certain value. Maybe it's this point over here. Alright, we call it k2 for the new output. Alright, so as you can see, the initial input plus the initial output, and then plus the new input, alright, meaning the feedback input. Maybe I should call this as a feedback input, right? Will give you the next round of the output, and take it as, alright, the input, the initial input of k1, alright, plus the feedback or new input k2. You get what I mean? So the initial one plus a certain new input system will give you a new output. That makes sense, because it's like an initial one plus a new one is equals to a new output, something like that. So we are actually we're actually adding up from the old information. The old information is k1, the first input, plus the new input will give you our new output, something of that meaning. I hope this is somewhat pretty clear. Now, this new input, as we say, is k2, right? is somewhat becomes the new plot on the input itself. You get what I mean? So for example, if I input k1, I plot it over here. Then the next feedback system that going into k2, I plot it over here. Alright, but because we are talking about, just now we are talking about only this term, which is only input k plus 1, this is why I'm talking about k2 only. Alright, if I were to plot in more points, right, if let's say for output also, right, for output, if this is k2 over here, then we should plot k2 over here also. Alright, so if we were to plot more points, so if I input k3 now, or for example I should continue. So if I input k2 in this case now, I'm going to output a k2, which is this one, right? And then I'm going to feedback in, and I'll create a new point k3. Correct? k3 is the new input. So this new input is also can be feedback over here, k3. And this new input will go into this system and become a new output, which is k3 over here. Alright, this new output is somewhat a new input for this case. I mean, this new output is an output for, you get what I mean? So later on I'll just do out k3, maybe k4. Alright, so as you can see, this input compared to new input is simply one step. Alright, one step lagging behind. That makes sense, right? Because this is k plus 1. So this curvature, for example, I shouldn't link them, but for example, is simply like this. So starting from this part onwards, describe this one. Alright, so this is like when t is equals to 0, this is when t is equals to 1, something like that. Alright, so they are actually plotting the same plot. Alright, therefore we are only looking at certain specific output points. Alright, certain points at each of this point, that's all. Alright, and it's totally different from the curvature that we want, right? We actually didn't draw. And this drawing of the curvature will all go back to the Euler's formula. Alright, for example, this is the forward Euler's formula, alright, describing certain x dot t. In our case, maybe it's u dot k, and then this is u. If you still remember, if I represent the u, alright, I'll just show you. So remember, we have this transfer function.
So y to y has to sys. So in this case, we are in.
If somewhat this form over here, then we sub in the Euler's formula for this two. You still remember? This is the same thing that I'm actually writing right now. Okay? But what I want to convey is that this thing is just plotting points. They are just plotting points and summing up the points. Alright, for the Euler's formula itself, u dot k helps us to plot. It helps us to plot the continuous system. If you still remember, u dot k is simply taking, or in other words, taking this point, this output, minus this new output minus away this output, divided by its time interval, right? You get what I mean? So for example, if a new output, for example, is k4, minus away its k plus 1 is k4, which k is therefore is k3, right? Or in other words, if k is k3, then k plus 1 is k4. Alright, I'll just zoom in. So by applying the Euler's formula, then if you divide by the time step t, you actually form a curvature over here. And this is only for k4 and k3. If it's k3 and k2, then it's this graph. And then so on and so forth, k2 and k1, and k4 and k5. So you're gonna plot. So this plotting is not this plotting of the graph, the curvature, is not shown over here. This is only plotting the points. If you still want to go back to plot the curvature, you're gonna take this new output divided minus this output divided by its own interval, this time step. Alright, maybe this is when this is 2t, this is 3t, this is the period, right? So this is it. Alright, so I just want to make things more clearer is that this equation that we've derived is only plotting the points, while the Euler's formula itself is to help us to link the point together into a curve. That's all. Okay? In other words, this configuration, alright, is different from this configuration, or this one. This one, if you were to sub in the Euler's formula, it will become this, right? And this one is different from this one. Okay, you can rearrange, and when you rearrange, you're plotting the points already. Okay, I may be wrong, but what I feel is that if this is u dot t, right? As we say that u dot t is simply is just drawing the curve between each of the points k2 and k1, and then the next round you'll plot k3 and k2, and you'll eventually plot a point. I mean a slope out of it. Alright, but is simply also the input itself. Alright, ut is the input. This one, ut is the output. This one is simply the plotting of the output. You get what I mean? Or in other words, this is the actual output signal. This is the signal will be a time step faster than this. So for example, this one is the initial output, and if it's feedback, for example, initial output is for k2, and then in feedback it becomes k3 at this point. Alright, but however, we're actually closing up them together. So this curvature, for example, for example, this is the initial output. Alright, the first output lah. Alright, this is the graph plot. Alright, one time step later, this is over here. You see, so this portion over here is faster, is one time step faster than this. You get what I mean? If let's say this is t, this is 2t, this is 3t, this is 4t. Alright, now this is t, this is 2t, this is 3t, this is 4t. As you can see, this particular t and this particular t is a different point, right? Because simply this graph itself is moving faster than this one. It's just showing the plot. Alright, it's just showing the plot, that's all. Alright, well, this one is just showing the points. I hope this is somewhat intuitionally clear. Alright, something like that. Same applies for this case. It's exactly the same as this one. Alright. Lastly is that this is the initial output. For example, this is the one time step after this output. Alright, it is just one time step outside this output. In other words, they are actually showing the same graph, just that it's showing, for example, this is showing in terms of 2 seconds. At time 2 seconds is at this point, while this graph it shows at time 4 seconds. Alright, this point at 4 seconds of this graph. You see, when it is 2t, alright, this is only at t. So this graph is 2 seconds faster than this one. That's all. I hope this is pretty clear, and therefore this whole chunk of the description describes in terms of graph. This whole chunk over here describes in terms of points. Alright, I may be wrong, but this is how I understand. And before I forget, this is it. I shall see you in the next video for examples.